Okay, so a little introduction. So robotics is a very popular term. I did this Google search a few years ago, and it's not totally reproducible, but roughly the story is the same. If you enter this into Google, you get this kind of page, very typical. And then these are all humanoids, right? Which are totally useless toy robots, but that's what they all are, right? And I think at that time it was on page 2 that you had a little legged robot up there. Where's my cursor here? Up there. And this is actually even not a normal regular robot arm. This is a special compliant arm. And I think on page 4, there was a vehicle up there. And then on page 4, you had an industry robot. And that might be different now. And of course, most robots in the world are industry robots. That is not autonomous robots. I'll say more about that. The huge majority in these autonomous robots are very special subfields. And this course is about autonomous robotics. I'll talk about that in a little bit. But that just shows that this robotics idea is very much tied to human-like behavior in the popular culture, right? And that's what people think, like these movies and so on. And originally, the word even comes from a play, where somebody imagined a human-like agent that would look like a human, behave like a human, and so on. So this is part of the fascination always of this topic. It's not very much the reality. Now, this course is about autonomous robots, and those get, they're not human yet, but they are sort of a theoretical answer to problems in artificial intelligence. So industry robots are programmable machines. That was the feature, that they are flexible by being programmable rather than have a fixed function. But the information is given to these machines by the programmer, right? They don't have perception of the world. They're not basing their action on their own sensor information. For instance, the robot arm in the production chain would move to a location, and if the part is at that location or not is then up to the factory to make sure that that's the case of the engineers. We had a project many years ago with Daimler, the Mercedes-Benz company, where the autonomy consisted of the robot arm having a little bit more tolerance for how precisely the part is positioned. So they had some camera, and then if the arm was like a centimeter off, they would compensate for that. That was then their notion of autonomy, very limited. So autonomy, the word comes from giving, nomos is law, giving yourself the law yourself. And what it really means is the notion that you're generating action, behavior based on your own sensory information, typically on board. It could be also, but from sensors, and you decide about your action based on that sensory information about the world. Now, again, this is ultimately part of the artificial intelligence vision. So, for instance, the classical textbook of AI, Russell Norvig, is of the standard textbook in that area, has in the introduction this sentence here, that the unifying theme of AI is the idea of an intelligent agent, an agent that receives percepts from the environment and performs action, which would be an autonomous robot, right? That's sort of the original vision, even though in practice it's not always been like that. So yes, so autonomous robotics is part of AI in that sense, right? But as you will see, it has more than AI systems because it has all these physical aspects as well. Now, so that is easily said, but then if you look more precisely, then some of you engineers know there's autonomous control, which is the idea that you physically influence something, a mechanism based on sensor information, right? And actually almost every aspect of control has that feature, that has sensors and controls based on sensors. So that's not supposed to be autonomous robotics. That's supposed to be just control. And so roughly speaking, this means that the autonomy in autonomous robots is supposed to go beyond that. And that's not entirely easy to formalize what that means. So roughly speaking, it means something like decision-making. And decision-making ultimately means a qualitative change. In control, you essentially have small signals, small response, so stability. And that would mean that you're just adjusting something in a graded way. And decision would mean that a small change can lead to a macroscopic change. You know, simplest, if you avoid an obstacle, you have to turn on the left or to turn to the right, you know, to go two ways, maybe to go around it in the plane. And then that's a decision, turn left or turn right. And it does actually really does have consequences. For instance, would mean that if you decided to go left, you better not change that opinion again next moment in time. That's a real problem in autonomous robotics, to stabilize decisions, because if you change that, you can imagine that that will not work well, because then you might oscillate into the obstacle. You know, and selecting the object that you reach for, that will be a decision. Well, if you're just looking at one object and you're controlling the precise grip, then you would say, well, maybe that's control. To formalize that more generally, again, is a little bit difficult, but that could be maybe the most elementary form of distinguishing between that. So that's what we're talking about. You know, there is perhaps often an intuition, you know, like these humanoids and the robots in the movies, where that autonomy goes very far, and the robot does whatever it wants, right? And that is actually not at all what actual autonomous robotics is about. Actual autonomous robotics is about giving the robot tasks, not the robot figuring out itself what to do. We actually, in one of our industry collaborations, we had these people saying, "Oh, you're crazy! The robot decides itself. We want to know everything the robot does, you know, and have control over everything. But you know, maybe it can have a little bit of freedom, and that, if you look at it that way, then you know the robot needs to get commands that give it tasks, and you could say they are actually really ultimately just there's some sound because the robot is speaking person. This the fetus who was my group leader about 2 years ago. It was very low levels, like 20 years ago. And so one could actually say autonomous robotics is actually about having a high level at which you give a robot tasks. Now, the programmer would be telling the robot exactly which parameters, exactly which grasp, and so on. And then if you can give a task to the robot by just talking to the robot or pointing at an object, and the robot then acts on that, then you're using that autonomy, the fact that the robot has sensors and can you know, maybe distinguish between different objects based on its own perception and so on, as a high-level interface to that programming, right? So it's programming by human-level communication. And that's not an unreasonable perspective on autonomous robotics. So there's quite a bit of that. So maybe first to give a little impression, I have a few slides where I have just some photos and little videos of robots. I'll come back to that in the end. I'll make a more formal list of typical kinds of robots, and you get a little sense of it. So there are simple vehicles. I actually own even one of those vacuum cleaners. This is mine. It's actually, I have a new one now. It used to be mine years ago. And you know, this is a couple of years old that I made that slide. There are all kinds of things. They are commercial, right? You can buy them. They're actually quite good now. I mean, men typically think they're good, but some women who think they're not good. It's an interesting topic. But they do simple tasks, right? And so this is commercial level stuff. There's much more of that now. These are vehicles. I'll come back to that. It's important. Here are robots my team's built, and I'll come back to the two of them. We actually built an autonomous wheelchair, which is really cool in that it was really low level, really cheap sensors, which still didn't get it to be a product because of all kinds of complications in that market. But the others are just experimental. We'll come back to these later. And then, you know, all kinds of other kind of vehicles, and you know that autonomous cars are robots, right? Because technically speaking, that autonomous driving is robotics, and that's a whole field. I worked a little bit in that field for a while. I can say more about that. Maybe I'll do that actually off the record in a exercise session if you're interested. I'll not really teach about that. Then there are these, you know, vehicles. I will address it a little later. Vehicles, so they're vehicles and arms are categorically different. And roughly, I always say the difference is vehicles are robots where the sensors move with the action. The actuator moves the body around, and the sensors move with the body. For instance, if you put a camera into a robot hand, then that robot hand is a vehicle. That's how we define that. And that has real consequences for control. You can control a system where the sensor moves with the actuator in simple ways. For instance, you can just say, I want to move it so that red stuff grows on my camera. And that way you will approach something that's red. You don't need to estimate where it is. You don't need to estimate the distance and so on. So that's called visual servoing. It's a manner of controlling. While arms are robots where the actuator and the sensors are separate. Like you have a camera and then you have an arm. And that requires much more sophisticated kind of perception. And in the animal kingdom, almost all animals are vehicles. Most animals do the action with their body, with their head. Dogs, for instance, do most of the action with their snout, with the mouth, and they dig it with their mouth. They do a little bit of paw action, but not very good. So we humans and some other monkeys are the most manual, who do a lot of work with our hands, where the sensors there are some sensors in the hand, but the important vision sensor is not in the hand. So that's vehicles versus arms. In the course, we'll have that. We'll have a lot of work on vehicles and on arms, categorically different. So legged robots are vehicles, even though their legs are sort of like arms, but they are typically not directing their legs at objects and do very special things. They're just sort of, you can think of the legs as being samples on a wheel. If you had a wheel and you don't fill in all the details, you just have sample spots on the wheel, and then instead of rotating the wheel, you just put your legs into the right places, right? You can see the analogy. So these are vehicles, and there's a whole area of work. A lot of these are biologically inspired. This is more for research purposes. And then there are specialized vehicles like crawlers or climbers and things like that. And these very specialized designs are interesting because it's the limitations that we have on autonomous robotics make that the special purpose ones are the most successful ones. And there are some really good applications, for instance, for robots that clean or even just measure stuff in underground tunnels and purposes, things like that. And then there are boats, underwater and surface water drones. And then, of course, there are drones. Most drones that you now hear a lot with the warfare what's going on in Europe are actually not autonomous. So autonomous drones are special subclass, but there are some work on that as well. But be aware that almost all flying is not actually doing obstacle avoidance. The most elementary form of autonomy is obstacle avoidance. And that is something that almost all flying objects don't do. It's just manual or control. Somebody keeps track of all planes and tells you how to go. So even obstacle avoidance is still a topic of research in this field. Yeah, and then the robot arms. Now they are work on hands, very primitive so far. So I'll say that in a moment. Interaction with objects is a real problem in robotics. I'll come back to that. So this is an arm that we have downstairs, and we're not actually doing a lot of work with it now, but it's a very cool robot arm that has torque sensors and is sophisticated. And this is the old version. We no longer have that here. So I think took it. Or is it maybe still here? I don't remember. The old version was like a home-built version of this top one. And then you can actually put a arm on a vehicle, and then you have both. And that's sort of the holy grail. Like these humanoids are supposed to be like that. They walk around, they are a vehicle, but they can also grasp. Now you might see all these popular movies about humanoid robots, like the Elon Musk show and all this. This is always just a vehicle, and then they waves the hand a little bit. They're not actually able to direct grasping action at objects. So actually, as arms, they totally use it. And so that's differentiated. Okay, so just to put that in your mind, and then I'll show you at the end of the lecture, I'll show you the handbook of robotics and the classification of robots, and you can have a little bit more of an academic grounding here. So why do we actually, why are we interested in autonomous robotics? As I already mentioned, it is sort of the holy grail of AI. So the original vision of AI was to have these autonomous agents that really act in the world, not just software agents, right? That really do something in the world. And why that is when it's purely intellectual, right? It's just an idea that can be debated. So I have actually done a little bit of a formal study at some point. I mean, not a scientific, but I made a systematic effort to ask people what they think. Got these kind of answers is cool, or they can do serve drinks and stuff like that. And then robot soldiers is the most reproducible answer I got, which actually makes sense. I'll come back to that. So in practice today, autonomous robotics is not deployed except for vehicles. I come to that as well. Actually, the most deployed are toys. So somewhat useless in the sense, don't do anything physical. They just have a body and do things. There is surprisingly much interest in that. There's a whole research program at the EU level about robots for autistic patients who, for some reason, which I'm not sure is understood, have an easier time to play with the autonomous robot. I mean, most of your cases, then you might be familiar with, where that is viewed as a possible way of how to make them a little bit more active, these people. And there are some ideas that elderly would use robots. I don't know what that is. But so that's kind of easy because the task constraint is not very serious, right? Just as long as it does something, is a bit reactive, it might be fun. So that's a whole branch, and there used to be some of those were on sale. Some of these products, like the Sony dog, maybe no longer known. And then they went out of sale because what typically happens with these things is that because the behavioral repertoire is so limited, it gets boring quite quickly, and then people weren't really buying it as much. So that's one line. The other line that's very prominent is this toy issue is quite prominent in Asia for some reason. I don't know, some cultural affinity perhaps. Here in Europe, there's a lot of work on assistance robots, so robots who interact with humans and support humans. So this sort of very typical social thinking in Europe. So a lot of the funding programs in Europe are around that. So at work, assistant robots and even home care and so on, very far from being deployed. In spite of, I've been in projects where in the end of the project, we'll have this prototype now. It's never really worked. So this is a very, very difficult problem, and you'll learn a little bit more in the course why that's so difficult. Military is in a sense, most rational application, because in the military application, you're not having the human there makes a lot of sense. In other cases, it's a very question if you just because of, to eliminate a job, is that really what you want? Like a caretaker, you want to eliminate the job, is that really worth it? But in the military, of course, it's very interesting to take the human out of the battlefield. So that makes a lot of sense. And the autonomy aspect is interesting because remote control is vulnerable. And we see this now in the Ukrainian war, that there are countermeasures and so on. And so there's a lot of research. The US has been leading, and maybe other countries which are not open. And there's been serious investment into this. In Germany, somehow it's taboo. Germans have a special thing that we somehow pretend that we don't need the military. And I'm not teaching about that. There's a famous person in the field, Ron Arkin, who developed a particular approach that I referred to, who actually did a lot of work with the military, and some very interesting stuff exists, but it's not very well known. Some of it is published, but not a lot. So these DARPA challenges that some of you might know about, that a lot of YouTube videos are about that. DARPA, it's the American funding agency that is actually funded by the Department of Defense, but they defined robot competitions that are not military in nature, but it's sort of the idea to stimulate work that would then ultimately lead up to the military. So they are driven ultimately by that vision of making military robots. And interesting ethical issues I'll not talk about. When you say decision making, who makes the decision? Is this still a human? And I can tell you that when I was in the Navy as a young person, we already had a mode like that this is like in the 70s, that a ship in a certain battle configuration has to fire at aerial targets, rocket attacks, autonomously, that is faster than a human can decide. And so you get into special mode. I mean, it wasn't not high tech from the current point of view, but still some form of decision making by an algorithm. And so is not just a very recent problem, but there is some real work on that right now. So autonomous vehicles are the one case where there is, this is actually a bad example because the Amazon warehouse has very, very limited autonomy. The only thing is these robots stop when you step in front of them. But all the motion planning is actually done by a central controller, and it's not autonomous. So it uses some cameras for some supervision, but it's one of these little platforms are the ones that are really deployed in large numbers. But autonomous driving would be, of course, a form of robotics, and that is really using it as a vehicle, a vehicle where you don't need a driver, and it is close to deployment, right? And it's funny because I've been working. I no longer do this, but for a long time we had a driver assistance group here where we were doing driver modeling, and we had a driver lab here, and we left that field because we felt that the basic research in university was done, and now it's all done by companies, which is largely true. But then it turned out it's still not, actually still not true. I was in a certain kind of committee at Volvo. The Volvo trucks and Volvo cars have a joint research company where it was more about driver modeling, and we really saw the discourse change from saying, "Oh, autonomous driving like in 5 years, in 10 years, in 5 years, and then maybe later." And so currently, I think it's still a bit unclear if we get there, but in special cases we get there, right? There are autonomous vehicles on factory floors or in special environments and so on. But so the problem is always this last percent or 0.5% of cases that could lead to accidents that you're worried about. So that's maybe the only area where it's really the product itself that is the goal, right? In other cases, it's sort of indirect. So the truth is that it is so far just a research field. It's a playground for research, and there's some intrinsic reason why that's interesting. And this course is more about that. It's not about applications of autonomous robots. So it's an interesting research field. This was from one of our projects where the whole point here is that the robot, the object is moved just a little bit while the system is grasping and can adjust to that. And that is a huge effort to get that right. This is actually a case where this is just a big dynamical system. So there is no program other than numerically solving the equation. And it can still do these sort of discretely looking things. So that's really academic, right? That's a research as a principal question that we study. And so that's interesting in a way because it captures some fundamental challenges in engineering. So one of the modern forms of engineering that permeate all of engineering is essentially that you model everything until what is not modeled is only noise, and then you have a good theory on how to deal with that. And that's where autonomous robots are an interesting challenge because you could say almost by definition, you're saying an autonomous robot operates in an environment that I can't model. If it can be modeled, it's no longer autonomous. Then I have the information about the system, or I have some. I have some parameters that I need to estimate, perhaps. But other than that, everything is not. And you could say, well, natural environments are defined as environments that I can model, or where the model is very good. And one component of such environment is a human being. If you're interacting with a human being, it's very hard to model a human being because they behave in a funny way, and it's difficult to limit what this human does, and therefore interacting with a human requires working in a place where you don't have these very good models, right? I mean, you still have models, but not as good. And so addressing that challenge is one of the motivations of doing autonomous robotics. And the other is ultimately system integration. So robots consist of a lot of different things. I'll come to that in a moment, and of very different kinds, and they all need to work together. They are a very good exercise in that. That's one reason why you often see student projects being about building autonomous robots. Some of you might know there's this robot soccer league, and there are robot vehicle competitions that are often run by, so it's teams of students from universities that compete there. And one practical, didactic motivation for that is that the students learn system integration because they have to build the hardware, the sensors, the computing, the communications, and the programming, and so on. And all of that needs to work together, and that's that's a very good exercise. So, robotics, autonomous robotics, is inherently extremely interdisciplinary. So, certainly true about even just the hardware. There are very different kinds of hardware in there: digital, analog, sensors, communication, networking. But then also even going to like human factor things, safety issues, even ethics issues, the whole energetics, which I'm not going to talk much about, but it's real constrained, how much power you need, for instance, prosthesis work with the idea of having intelligence prosthesis. But if they use a lot of energy, they're heavy, and you don't want to have to tell the person, oh, you can only use it for 2 hours, and then, take off that arm and take your old arm. So you see there's a lot of challenges. So it's a very interesting research field. And that's really what it is. Good. That's a bit background. Now, in the rest, I'm going to a little more into the research and then pointing to what we actually talk about in part during this course. First of all, just as a matter of clarifying terms, I'm speaking quite quickly in this introduction, right? This is not something that you're supposed to all have to remember later on, but interrupt me anytime, right? I know it's hard to do, but feel free to do that. So just for reference, because I will sometimes talk about that, refer to that, architectures. So architectures are ways of how all these different mechanisms are bound together, right? System integration would then be organized around an architecture. And this classical one that was developed in the 50s when this field became concrete, when people started to actually work on this, was the Sense Plan Act framework. It's not one architecture, just a general framework. And that is still very dominant in discourse and thinking. And of course, they're much more complicated now, but still, roughly speaking, it's still very much like that. So it's essentially organizing the robotic components along the sensory stream from the environment ultimately to the acting on the environment. And it's robot acting in the environment means it then senses the consequences of its own action as a vehicle directly because it gets sensor information, but even as an arm, it will see whether the object it grasped moved or whatever it is. And so it just follows the sensory stream, and roughly these 4 stages where sensing and acting are essentially the parts that are shared with conventional control, right? The sensors would be the sensors that we also use in control. And then the actors, were very good servo kind of systems and achieve certain physical states. And the intelligent part, the AI part, would be here, this inner part. And there was the notion that you integrate all the sensor information into a world model, different kinds, and that based on that world model, you can then do the intelligent part, maybe planning, achieving goals by planning based on that information. And then the plan is handed down to the action. So this, there was a lot of people saying that failed, even though, frankly, it's still the framework that we used. It was much harder than initially anticipated because historically, certainly the difficulty of extracting meaningful information from sensors was way underestimated because we didn't do that so well. It was kind of intuitive that you could do that, and people started with very, very simple worlds, the block worlds, where there was just some cubes that you would have to estimate the parameters of, but it didn't scale very well at all. And this is now still called a challenge of perception. I'm deepening that in a moment. And that made that this arriving at that world model was quite difficult. And that ultimately led to, my next slide comes to that. So that led to real changes in how people look at that problem. And in a way, they didn't notice the problem that exists at the planning level because the people who were doing planning were assuming they have a world model, and there was a lot of work on planning. And then the world models never arrived, so they weren't seriously tested, these planning approaches. And as things got better, people realized, I don't know if it's historically correct, but it certainly only became a more acute problem once we had some reasonably autonomous front ends of this, that acting, planning when you're actually physically realizing it is also very difficult. And that has to do with the interaction with the physical world. When in physical, when you're really having contact with the physical world, you ultimately have to update your plans all the time. When you catch a ball, right? When you don't just catch it and stand there. You actually yield a little bit, and take the energy out of, or the momentum out of the ball. And where you end up with the ball, that depends on how heavy it is and how fast it came, which velocity it had. And that actually means that you have to replan your final posture. It's not like you can have a plan for your hands and then enforce that no matter what. And this fact that planning and control cannot be separated so well is a real challenge. And to this day, and it's particularly important when you interact with humans. So that's why this fell a bit out of fashion as a theoretical approach, even though in practice it's still a component like that in every robot. So in the 80s, there was something that was called a revolution at the time. Rodney Brooks is the apostle of that. He went on to, he's actually one of the co-founders of that company that did this little iRobot, the little vacuum cleaner that I owned. I bought that because it was a really cool company. The main thing was it was quite cheap. But now he has a company that produces robot arms that are somewhat cheap. So he was at the MIT at the time, but there are a lot of other people in this domain, and they have this other idea that they would say it's orthogonal. I mean, his horizontal previous was vertical. It's a bit of just a cheat because I can just rotate this thing. But the idea was that you would have what they call behaviors, that is, systems that have direct access to sensor information and to do something physical, but that are themselves not very complex. They don't do planning and then very intelligent. And the intelligence would be just in how these different elementary behaviors, as they call them, how they interact. And there would be real limitations on what they can do. They couldn't just subsume each other. One can provide input to the other, some special restrictions on that. But other than that, it would be always a very simple system. So biologic would be sort of a reflex-based idea that you would have very elementary action perception patterns or reflexes, and then you just combine these in an intelligent way. But other than that, you just you don't introduce intermediate stages. You don't have a world model, for instance. Every behavior has its own little perception, only for what it needs and not for anything it doesn't need. That was initially very successful because it did lead to very quick progress towards some simple vehicles. And I'll present next or in 2 weeks this little system here, which we built in Marseille a long time ago, which is extremely primitive. It had like 100 lines of code and actually really performed pretty well. It was looking for light sources and doing opposite ones. And this is a laboratory thing, but there were some successful stories with that. The problem was they didn't scale so well. So if you want to make the task more complex, then ultimately the old problems were still there. And so it has faded a little bit as a revolution, even though there's still people developing this. And actually now the state of the art is that these behavior-based systems are always included. Typically, you have a complicated architecture that does all kinds of world modeling and reasoning, classical AI. And then at the interface with the actual world, with the sensors and the actuators, you have a little behavior-based system. So it's like a filter for the low-level stuff. So this is actually this architect whom I mentioned who does some military work. So this behavior-based stuff is very real, but it's not the only thing. You pretty much have both. So I already hinted that there are remaining challenges. And if you go to a robotics conference, there's discussion about how many and are they all different and so on. But roughly speaking, perhaps these 4 areas could be viewed as the areas that are most challenging at the moment. So the one is perception, I already mentioned, and I'll step through these very quickly. So I should just say this because I assume some of you don't even know what perception is other than the daily life word of perception, right? And so perception is really about the world, estimating something about the world. It's not image analysis. It's not looking at the stimulus. Now, sometimes in the laboratory in psychophysics, you ask people to do very simple things, such as detect a line or the orientation of a line and so on. Then it looks like it's about the stimulus, but that's not the case. In fact, the stimulus for you, the stimulus is the stuff that impinges on your sensory surface. The stimulus is an image, and what you're perceiving is not an image. You're perceiving people, right? Tables. And actually, we're very specialized in faces, so we're very aware of faces while not so aware of texture, for instance, some funny details here in the room that you might not actually pay attention to. So it's that problem of, yes, using sensory information, but really estimating something about the world, typically task-oriented. I flashed this little thing here, for instance, and then you might recognize there is the robot arm that I showed earlier. In a somewhat funny pose, you might be able to classify that, see that, and maybe not look at all the other funny details here on this table. Because you will also pay attention to the fact that humans who are very attracted to looking at humans. And you might also be able immediately to see that that's the same robot arm, just in a different pose, just in a different angle. So this illustrates you already three things about perception, namely that you are able to attend to things, that is selectively look at something, typically because you have a goal. Right here, I was kind of priming you to look at robots, and you saw that robot, and maybe you're looking then at the robot, and there could be many other. If you're looking for a extension cable, you would look at that scene very differently. There were a lot of extension cables there on the table. And so you're searching for information. It's actually not that you're just sitting there and the stimulus comes in, right? You always some task in your mind. So that's one area that is not very well developed. All this deep network stuff. They call some of them, transformer networks claim they have attention. It's just a different use of the word. It has nothing to do with this kind of attention, spatial attention. So this is something that current computer vision work, in spite of all the progress with deep learning and transformers, is not good at. But there's a lot of work on that. The other is detection and classification. That's where they are much better, even though these systems will not typically be good at localizing and segmenting the object. And then the third is pose estimation. When you interact, then you have to estimate not just that it's a bottom, but also really how to grasp it, right? That will be ultimately figuring out how it's oriented and how to best, where it's located and so on. So this is still a problem. You can say sort of robotic vision is sort of orthogonal to the kind of vision that we now see advanced through deep networks a lot. That vision is very much huge numbers of data through internet-based images. So the training of these deep networks can take a very large number of different images and different instances of objects. And so they also deal with a lot of different objects, but then they're not dealing in depth with them. They can't really handle them, can't predict what they will look like if you rotate and so on. But in robotic vision, it's the other way around. You have a very limited number of objects that the robot is interacting with in a concrete scenario. You might have maybe 20 objects that it ever encounters in the workshop, let's say. But then a lot of experience on those, and also a lot of demands on those to be really able to see them from all sides at all distances, and then to estimate their pose and maybe make a precise distinction between screwdriver number 1 and screwdriver number 2 if it was working with human tools. So robot vision is a bit different from that generic computer vision. So that's continue to be line of research. I should say, so I'll not teach much about that in this course because it's more the topic of my winter semester course. There will be a little bit about perception for vehicles. I mentioned initially vehicles a little bit different. That is, you can make progress in making planning the motion of a vehicle without necessarily having that same high-level perception of estimation and what I just hinted at. And I'll give you a little bit of a flavor for that. And that's actually one reason why the vehicles are more developed, are closer to deployment than autonomous arms. So in vehicles, the core perceptual problems are navigation, knowing where you are, and that refers then ultimately to a map, and then actually getting the map, right? It's autonomous if it itself maps the environment. These two things together are sometimes called SLAM, self-localization and map formation. And the other very elementary one is avoiding collision. That includes a collision of something that you don't know what it is, just you don't want to collide with it. SLAM is a very intensely studied object, and some people say it's solved. I mean, theoretical approaches how it's solved, and there are some practical ways it's solved, but still ongoing work on it. But there's been enormous progress. This progress comes from using probabilistic methods, Bayesian kind of methods. A German, actually, Sebastian Thun, is a major contributor to that. He's the guy who ran the Stanford car that won one of the DARPA challenges, and he's actually now running mostly remote learning universities. He's driver of this called Audacity or something like that. It's like a remote teaching system. And he had two colleagues, Burkhard and just blanking on the name of the third, Fox, yeah, Peter Fox. So three Germans who really pushed this field ahead. Maybe not sure. Two of them then went to the US and the other to Canada. Only Burkhard is still in Freiburg, but they are really major figures in this field. And so that there's some good sense for that. And obstacle perception made a huge step forward with the arrival of depth sensors, essentially time of flight sensors that are very precise. Here's an example. So range images, maybe not very clear, but you can, with a laser rangefinder, you can get a depth profile. So you essentially have a 2D map where the third dimension is just the depth that you measure. And that is just a very, very good source of information about obstacles. So an obstacle, once you don't need to know what it is there, and if it's a one object or two objects, you just need to know if it's free, if you can go there, right? And so the depth map is all that you need. And so we'll be, I'll not talk about the sensory basis of that, but we'll be studying motion planning in vehicles as one exemplary thing that I'll study a little bit more in detail. I did my own work in that area. And one can say the perceptual basis of that is now in a very good shape, even though we didn't use laser rangefinders, but we used other kinds of distance measurements that are less precise, but still good enough. So in a way that the perceptual problems there's been a lot of progress on that, and that's why the basic properties of autonomous vehicles are in a much more advanced state than in arms. Okay, so that's a perception. So perception for arms who are orienting the actions at objects and manipulating objects is still a problem, and for cars it's a bit less of a problem. So related is the interaction with humans. Yeah, interaction with humans means also communicating with humans, as I initially hinted earlier. That's actually the most practical use of autonomy, to be able to interact with a human, taking commands just by a human saying something. And that actually connects to some profound problems, ultimately to what's called the perceptual grounding of language, right? When you talk to another human, like, give me that bottle, or, where's my pen? Then the human is able to know what you're talking about, right? Like this bottle really concretely. Try that with ChatGPT. ChatGPT just gives you some other phrase, that it knows when that phrase comes, then typically people say that doesn't know at all what you're talking about. Wouldn't be able to point to the object or know, in the image which object you're referring to, even though people are working on things like that. And so this is sometimes called joint attention, that you're able to, in your communication, to refer to the same things in the world, and not just on the table, maybe also to the same event that happened a while ago. That screwdriver that I used there, where is it now? Then it's already quite a complicated task, right? You need to know there was an early event where a screwdriver was used, and this one I'm looking at is not the same one that was used earlier. You have a memory trace of what happened to that screwdriver. Here's an example from our research. We actually do work on that, like the red cup to the left of the green cup, right? It's this one, right? So this is a case where there are multiple possibilities, and you might even have to do some reasoning to figure out which one. It's not maybe very plausible humans would use that kind of a language, but a lot of communication problems are of that nature. That is, we humans are very good at knowing what the other person would know, so that we only need to give that information that then makes a difference. So to do natural communication interfaces with humans really means going into cognition understanding. Sometimes there's a notion of intention perception, right? If I have to explain the robot in a lot of detail, then it's quite annoying. I have to be able to, for the robot to have a good way of figuring out what I intend to do, what I want it to do. So again, I'm not teaching about this in this course. In the winter semester, I used to teach about aspects of that. Physical interaction. So this is getting closer to what we'll actually be talking about. So physical interaction with objects. So that's when you actually touch or even try to transmit force or transform an object. And that is a famously difficult problem. There is a theoretician whom I happen to know, who's old now, Doyle, who proved a theorem in the 70s that still haunts us. It essentially shows that in a very general sense, control is not robust, meaning that a small misestimate leads to large deviations. And that's this problem that that the separation of control and planning. Now, control would be a parameterized action plan, and then the control is just realizing that plan. And that model breaks because if there's just a small error in the plan, then something catastrophic happens. And you might know that industry robots, if there is an like if a part is not positioned right, the robot would use all its force to put the gripper where it thought the object is and maybe destroy the object in that way. And so that's a real problem. And give you one example, you know, milling. It's called, now I forgot the German word for that. It's like fräsen. Fräsen, exactly, thank you. Actually, I used to not know the English word, now I forgot the German one. So fräsen is not done by robots. There's a lot of research on doing that with robots, but typically the arm will become unstable. You know, milling means that you're taking off some of the material to make like a ridge, or to dig what is it called? I actually don't know the English words for this kind of stuff, and nor the German ones. So transforming material, and then you can imagine that as you're transforming the material resists to different degrees, and then depending on the properties, the whole system might get into an oscillation and leaving a not very clean trace on the object. And so there is research on doing that. So typically this is done by specialized machine. In Germany, there's a very strong tradition in building these kind of machines that are not so freely programmable. Right? And doing it with a robot would make it much more flexible. And so there's just a little pointer at the fact that when robots interact with objects physically, then that's not so easy. So most of the robots do some painting, they do some soldering, which typically means just getting close to something. Then you do some like high temperature or create high temperature in some way. And then hoist things if they have a hoist point. Hoist point would mean a place where there is something to grasp the object, and they can then move it around. And that's a very limited physical interaction. Anything else is still very limited. There are some famous cases where it's actually a human who guides a robot. There's a robot that is compliant. That the human is the compliant part, that is flexible. A famous example of that was the space shuttle. If you still, it's ancient, but actually still the same problem persists. The space shuttle used to have these robot arms. There were two arms. One was German, actually, the DLR, and the other was Canadian. You remember the space shuttle? Maybe you're too old, too young for that. Yeah. So it had this huge arms, very expensive object in space. it's getting a bit specialized, but you know that when you are moving an arm around, right? The angular momentum is conserved, right? So that actually angular momentum flows into the ground or whatever your robot is screwed onto, right? And on the Earth, it's not a big problem, but in a spaceship, then the whole spaceship can start to tumble if you're moving a large arm around, right? So this was an interesting challenge, and there was a lot of work on the control of that so that it would minimize this sort of thing. It would still have that kind of effect. And so the notion was that the spaceship would go and grab a satellite and then bring it in for repair or replace it with some other one. And it turned out that this grabbing it was very hard. And there was a time when it was achieved by a robot, a human, an astronaut, being connected to the arm and like with some shoe connection, and actually catching the satellite and sort of wiggling it into the mechanism for control, because the humans are very good with this kind of wiggling compliant action. Huh? Compliant ultimately means that you're updating your plan as you are sensing physical resistance. Not sure if that's no longer exists. I don't know what the current state of the art of catching satellites is, or if that's even attempted anymore. So that's an illustration of a really difficult thing. And if you want to have autonomous robots that really do something physical, you have to deal with that. And one thing of doing something physical would be with a human, right? Maybe like the idea of lifting a patient, or helping someone to get up, and like in prosthetics or assistance robotics and so on. And that would require doing that, for instance, doing it softly, not killing the human by misestimating exactly where it's positioned. So that's a topic of a lot of research, and just summarizing what I'm saying. So this fact that robots are so dangerous has to do with that, right? Robots are very strong. They are very strong typically because of their limitation in control, right? Their own action creates disturbances, and they have to counteract these disturbances, and they need to be strong to do that. But then if they misestimate and there's a human in the path, they can kill the human. And so they're unsafe. And so doing this in a more human-like way would also solve that problem. And so one approach is soft robotics, is a strong field of research. So where you make the actuator soft in principle, you make it weak, and therefore couldn't hurt, and therefore can have some built-in compliances. If you don't quite figure out the right position, then at least you're just going to just be deformed a little bit and then still act. And that's how we are as humans. We have muscles. Muscles are weak. And in a sense that one can make precise. And that changes the nature. So I need to limit how much I say about that. We'll have a whole lecture at the end of the course about that, about how muscles are weak. And so the fact that muscles are weak means that we don't usually hurt ourselves, right? You can run into stuff, right? If you fail on obstacle avoidance, I fail all the time. Cups, throw them over, and so on. But usually I don't break my arm because the amount of force I generate is limited by the fact that my muscles are relatively weak. And so that is fundamentally different. That means, for instance, that control and planning are not separate. We're actually planning a motion, and then as there is resistance to the motion, we're replanning very quickly. We do that all the time. And this ball catching example would be one. It makes for interesting control problems. And so once you have a weak arm, you can't actually just give it a plan and then just minimize the deviation from the plan. Then the deviation will not be small. And so you can't realize that. And so you have to take into account how you will control it from the very start when you plan. So one example of that is upright stance, right? We're standing upright. I'm standing quite comfortably here. And it turns out I actually studied that for some years in humans. And it turns out that this is actually a very active process. So standing upright is a movement. If you take a robot like Asimo or one of those, they just stand there passively. That is, all their joints are so stiff as an electrically controlled motor, just stiffen those, and then they stand upright. As long as the center of mass is over their feet, they will be stable. That's not the case for us. You can think of the muscles as springs. They are spring-like, elastic. And you have a spring constant, right? That tells you how stiff it is. And if you think of your body as a pendulum, it's an inverted pendulum, it's attached at the bottom, then that has also a spring constant, right? A pendulum and a spring have the linear law of force against elongation. And so you can say there's a spring constant attached to the inverted pendulum, and that's a negative constant, right? Because it would fall over. And so what you could say, roughly, to stand upright, I would have to have that the muscles that converge, let's say, on the ankle are at least as stiff or a little stiffer than that inverted pendulum, and then I would just be passively stable, right? If I lean forward, the muscles on the back would be exert some force by being stretched, and vice versa, and then I would be stable. And that has you can actually measure those things through some complicated procedures. And it turns out that the muscles that converge on our postural system lack in stiffness about a factor of 5. So they're only about 20% of the stiffness needed to stabilize the body. And so you can't just do that. So what you actually do when you stand still is that all the time you have sensory stuff going on that notices, oh, I'm falling forward, so I'm planning to move backwards, and sending a signal for moving backwards, unconsciously, quickly. And so in that sense, it's constant movement, and there's a constant shift of your intended position that is transformed to the body. I might even go, if I can do that, I will have a lecture on what is called the degree of freedom problem. If you have redundant systems, how you have many degrees of freedom. And the upright stance is an example like that, and we did very clean work on that, and I might be able to illustrate that. Yeah. So this is relevant to the course because in the second part, when I actually talk about arms, I will first tell you a little bit about technical ways to do that, and then I'll actually give a little bit of an insight of how muscles work, not the physiology of it, but just characterize them, and how reflexes work. And then we'll see how movement tasks are achieved by humans and other animals. And that's a very different style from the style that we do that in current robotics. So the fact that most robots are not so soft actuators, that they really have electrical motors that can be controlled very well, makes that they're very fundamentally different from human movement. And people are trying to emulate that. Good. So that's a big area. This was the physical interaction area, right? And then background knowledge is maybe the final frontier. So background knowledge goes back to AI. So it's still considered to be the core problem of AI. Got a little bit out of focus now with neural networks, with neural AI, where the people think maybe it solves that. I actually don't even think it does. So that's implicit knowledge, often not even formalized knowledge about the world, right? When you all have that knowledge, how to do something, how to open a door. If you have a robot to open a door, it's like a doctoral thesis to get it to open a door, and then you change the lock on the door and has another doctoral thesis to get that one, roughly speaking. So there's some physical knowledge of how to actually do that, and there is some kind of informational knowledge. Knowing that milk is in the fridge is background knowledge, right? And children learn that, and how to grasp a bottle when you don't want to spill it versus when you want to use it as a weapon, and all other things like that. I used to give this example of soccer playing, right? Soccer playing, of course, you have to know the rules of soccer, but you have to know, how slippery the ground is, how fast you would accelerate, how hard to hit the ball with side, or to tackle someone, how rough you would do that, so that you don't get penalized or something. And so this is sort of sensory motor knowledge that is really difficult to code and to extract and formalize. And this is the major frontier. You literally have projects where they have a cooking robot that flips a burger, and somebody really figures out how to do that. And if you take for instance, a pancake, then that doesn't work. You have to have another algorithm for the pancake because it has a different elasticity. There's an institute over there where they deal with conventional robots who work with food in production, right? And they throw sausages for them to land in a package, and they have to figure out like the sausage would oscillate. You have to figure out how to do that so it does land correctly, and that will be background knowledge, even though we don't throw sausages as much perhaps as those robots do. So that's pardon?
That's the most German thing I heard.
Yeah. Sorry, we tried to do a research project, but we came in with the human ideas to do this with compliant arms, but they wanted to do it at such high frequencies that all the human knowledge was useless, and they ended up just modeling the sausage. It's classical engineering. Okay, so that's a very classical problem. It shows up in all levels of AI. In AI, it used to be the idea to code all that knowledge, expert systems, right? That will be coding all that we know. And you can see how coding all the knowledge will be particularly hard for a physical thing, where you have to code things like, resistance and friction or compliance and things like that. So it's still ongoing work like that. Some people would think, well, now with the deep learners, that just learned all the knowledge. And that is not really true. That this is very limited what they learn. It's mostly in language, not grounded. That is just knowing. I mean, what the current deep learners primarily do is they can look something that looks like that statistically is like what typically happens, but that doesn't really say that it knows how to do something categorically different with that, right? For instance, just a description than actually doing it. That's a very different story. Anyway, I don't want to criticize too much. So when we write down a robot architecture, like behavior-based, you could say, in a way, that is knowledge, right? There's some knowledge in here in that for instance, that obstacle avoidance is the most important thing, right? If I'm a robot, I want to avoid an obstacle. Even if I have other plans, I also want to achieve a target, maybe stay on the road and so on. But I'm going to not allow collisions because no, that doesn't actually allow me to do the other things either. Right? I can just say, oh, today we'll collide. That's okay, as long as we achieve the target. Right? That's not what we do, except if we're planning maybe bullet movement of a bullet or something. And so in a way, there is some knowledge in that, right? And you could say if we figure out what the cognitive architecture of humans is, and there's a lot of work on that. In the winter semester, I teach a little bit about that. Then there is some form of knowledge, because the evolution essentially incorporates a lot of knowledge how things work, because it has figured out how best to organize our cognitive processes to succeed in certain tasks. So background knowledge can also be that classical problem of what the right architecture is. Yeah. And so the current work on that often takes this form of autonomous learning. So learning, already criticized a little bit, learning is often used for what happens in machine learning, which is in a way very supervised, even if technically it's not supervised, but it means the system is told this is an example, this is an example, this is an example, right? This is very, very structured. But autonomous learning would mean that you're behaving, you really have to have the capacity to behave, and then as you're behaving, you're learning, you're becoming better, and you're just sensing something that makes you better. Sometimes also called continuous learning or online learning. So there is a lot of work on reinforcement learning as an idea of that being a step in this direction. There's debate about that. Certainly not deployed. It's not something that works in the real world. It's mostly academic work. I'm talking about using that in robotics, right? There's some purely theoretical work, but in robotics, reinforcement learning doesn't work at the moment. And if it's the right trajectory, we also don't really know. So that's concrete research agenda to acquire that knowledge from experience. Now, if you know children, you've all been children at some point, you know that children take a decade to competently act, to even open a bottle or to do simple things in the household. It's learned and it takes a long time. And it's not just that they're waiting there to grow. It's really takes practice and their access practice. I have a small grandchild, and she plays kitchen, right? And she can do all kinds of things, even though mechanically she's not really able to do that. She just symbolically does that. If I ask her to actually steer something, the soup goes all over the place. So it's not that happens just from one day to the other that you know how to steer a soup, right? There's a compliant thing where you have to have the right speed and depending on the viscosity of the liquid. You might be familiar with that. Steering tea is different from steering a potato soup, right? Because different viscosity, and you do that, you can do that, right? But it was learned, something that's not so easy. Okay, good. So the perspective in this course is to emphasize sub-areas. So this is not a complete course of everything in alternative robotics, of course. It's also not a conventional that I give equal weight to the different things. I have a particular perspective that comes from my research. So it's a research-based course, but I also give some textbook examples, so a bit mixed. So I have a syllabus. So let me first show the syllabus here. Here. So roughly, these are the topics that are covered. Actually, I'm not doing the dynamic systems tutorial. I'll just do it in an exercise. So I'll talk about vehicles for about 3 or 4 lectures. I'll talk about a particular approach to vehicle path planning, so how vehicles move, and the attractor dynamics approach, which was developed in my lab. And then I compare that to other approaches. And then I'll talk a little bit about navigation. That is ultimately the SLAM problem, but not in a very technical way. I'll use that actually to make an analogy with human movement. And that's sort of a theme throughout. In these examples, I always compare how humans behave versus how these robotic approaches work. For instance, this attractor dynamics approach was used to describe human locomotion. I mean, the displacement, right? Not the leg stuff, but how you actually move around the plane, how you avoid obstacles, and how you go. There's used sometimes for describing how pedestrian traffic, right, how they behave. And the robotic version of that is the attractor approach. And then in the second part, I'll talk about arms, and I'll give a basic lectures just about arm kinematics and things like that. But these are just like a textbook, but then condensed into like half an hour. Like you get half of the textbook in half an hour. So in other words, it's just a survey. But then I'll emphasize some aspects that are, again, from analogy to humans. So for instance, I'll talk about timing and coordination. I'll talk about degrees of freedom, this redundancy problem. That's something that humans have particular solutions for. And comparing then these to the technical solutions gives some interesting insight. And then in the end, it will be what's called control, sort of dealing with muscles and forces and so on. I'll make the analogy between muscles and the conventional ways of control. So that's sort of the survey over what we do. And so the particular perspective is dynamical systems play a big role. So across the board, we will be using dynamical systems as the mathematical language in which to look at that. So that comes from the work I do in the other part, in cognitive science style, which also is based on neural dynamics. So the neural networks described as dynamical systems, and here it will be not neural networks that are described this way. It will be specialized dynamical system for these different subtypes. And so you will learn something about dynamical systems, or I'll reactivate knowledge you already have, hopefully. This is a major direction of research in this field. So Daniel Kodyszek is one of the pioneers and sort of a big name in this field. He wrote a very interesting article a few years ago, but I think it's impossible for you to read it. You can try, you can look it up. Just aside from his abstract where he lists sort of fields of research and he thinks that really developing dynamical systems theory is one of the the research challenges. And he means by that dynamical systems ideas that cut across all these different domains, that do not just control, where it's very traditional, but also do that in planning and even do it in the interaction with the environment, both perceptual and physical interaction. So that will be really the main tool in the course. And I'll review other people's use of that. So we use particular approach with attractors and bifurcations, but other people like the potential field approach use, I would say, simpler forms of that. And then, of course, classical control and the mechanics, the mechanical description of the physical dynamics of an arm. It uses dynamical systems in a more conventional sense of conservative dynamical systems. And I will not teach that in a very technical way. I'm not asking you to make computations and compute eigenvectors and things like that, but to develop a conceptual understanding and intuition for these kind of ideas. Good. The last thing I wanted to do is give you a couple of slides, and you can look this up then in the PDF, that give you a little bit of a sense where this then is as a special course in robotics. And what I took the handbook of robotics. It's the Springer Handbook, a famous book. The latest edition from 2016 has 2,200 pages. Now it's a really large book. And I'll just flash here the table of contents to give you a sense for what this field actually is, and then the little corner we're looking at, right? So the first part of the book is the foundation, so the techniques across the board, right? And among these foundations, well, there's kinematics, or the mathematical description of arms, of articulated things. And we'll get one lecture about that. You'll understand that. And then the second chapter is about dynamics, of the equations of motion of the mechanical devices. And we'll have also one lecture about that, but very macroscopic, just very simple. And not really much about actuation at all, which is in here. And for modeling, you have to be able to model the dynamics of the plan, and we just take that for granted. There's a whole field for that. And we'll have a little bit of motion planning, but most of the motion planning will actually be about vehicles, and we'll come back to later. Well, this is also about arms. And I'll give a very little part of that dynamics lecture will be about control, but I'll just say what PID is and very, very simple things. And this is, of course, a major topic. And then force control, we'll not talk about that. And then I will talk about redundancy, even though not maybe very much in the robotics style, but I'll talk about what happens when you have more degrees of freedom than you need for a task. And I will not really talk about architectures, which is a major topic. So these 12 are the fundamental chapters they have in here. So this is these 11 chapters are actually classical robots that is not autonomous ones. This is what's shared with classical robots, right? That are programmed, but you still have to deal with kinematics and dynamics and control and so on. Now, autonomous robots, among the foundational chapters, they have behavior-based systems, and I will be showing you robots that are roughly behavior-based in their architecture. So I'll touch that a little bit. I will not talk about AI reasoning models for robotics. Actually, Michael Bessier is a German working in Bremen who's wrote this chapter with I actually have some connection to these guys. They had a joint project with those guys, but I'll not talk about it. And actually not really talk about model learning, but I might have a chapter on movement primitives, which is from that group. I just don't know if I have that slot for the movement primitives lecture, but if I find a slot, then I put that there. Yeah. So that's the foundations, right? So the foundations, we cover about half of it, but very, very crudely, because usually these are many different courses that you take here. Now, the second part of this is about design, all the different robot designs. So I already showed you some, right? The limb system is a chapter. Parallel mechanisms is maybe like platforms. No, I'm not talking about that, of course. Robot hands is a topic. So I'm not covering any of these, just to give you a sense for these different things. So snakes and continuum robots are typical design. This is the soft robotics, so the muscle-like stuff. I'm not technically speaking about it, but I'll talk about actual human muscles. Biologically inspired and modular robots, and then wheeled robots. underwater robots, flying robots, and then there are what I'll call micro robots as a work on very special mechanisms that will be not conventional rigid body robots. So these are different robot designs, but we covered that a little bit, and I'll just use some examples, but I'll not work systematically on how to design robots. The third part of the book is about sensing and perception, and I'm not covering it. I just want to give you the sense, right? There is work on force and tactile sensing, inertial sensing, GPS odometry, sonar sensing. So a topic we've actually used sonars at some point. Range sensing, so distance sensing, 3D vision in navigation and for objects manipulation, object recognition, visual surveying. I briefly hinted, you can do visual surveying by putting a camera into the hand and then you simplify the grasping problem. I'll not talk about multi-sensor data fusion. And yeah, that's it. I think I might have missed something at the bottom. So I will not cover perception very much in this course. Then there is a lot of work on manipulation interacting with objects, surfaces, so manipulation tasks, contact modeling, grasping, cooperative manipulation, so 2 arms or more, mobility, so sort of robot arms on vehicles. Actually, Mark Toussaint is a former student here of the Institute who is now in Berlin. And then special haptics, telerobotics. None of this will be covered, right? And the fourth part, no, the fifth, is it the fifth part of the book is about, they call it movement in the environment. This is ultimately vehicles, right? About when you, what I call vehicles, when the sensor moves. So we'll be talking a little bit about motion planning. That will be the opening. Motion planning, obstacle avoidance. That chapter, actually, I might even give you an excerpt from that chapter as a reading. There is SLAM work here, and I touch that minimally, and world modeling, legged robots, wheeled robots, and rough terrain. And this is underwater robots. We'll not cover that, right? And then I think there's something about areas of drones, and then so swarms, having many robots. That's vehicle type stuff that is covered. So we covered a little bit of the motion planning of that. Robots at work means application areas. I'll not cover that at all. It's just interesting maybe to know, industrial robots, space robots, robots in agriculture, outdoors, construction robots, robots for dangerous environments, for hazard environments, mining robots, disaster robots, surveillance and security robots, intelligent vehicles. So that's essentially everything. This is autonomous driving, medical and surgical robots, healthcare, human interface robots here, and domestic robotics, and then robots competitions, just this toy example that I mentioned. Right? That gives a little bit a sense. See the application areas, somewhat like what I mentioned. You can look this up later. And then the last chapter is about robots and humans, how they interact. So it has humanoids. This has to do with how to, in imitation, right? You estimate human movement, how to extract parameters for that to control a human robot. And then physical human-robot interaction. This is a very interesting topic. I was in a project review where it was about dancing, a robot dancing with a human. Just it's an academic problem. I don't know how to dance myself, but it was interesting to hear all the problems that arise, and that very subtle haptic cue somehow helps you to do something like that. This essentially is a form of prosthesis or exoskeletons, and then cognitive, how to intention perception and so on. Social robotics is a big field somehow. So I'm not sure exactly what it means. It's somehow with humans, and if humans like it or something. It's interesting. A lot of the time there are talks like that. And then socially assistive sort of overlaps with that. So there's something about learning. So this is essentially modeling so imitation, I could say. It's sort of like you're training the robot by giving a lot of examples. Oetbilia actually uses some of the methods that we developed here, but I dropped that as a lecture. It's too complicated. I think I have a slide maybe where I refer to that very briefly, but not really explain it. Auke Eisbert, they used to be married, by the way, but they're no longer. He is the pope of these biologically inspired robots. And again, I used to have a module on that, but I dropped it. There's a whole area of evolutionary robotics where the notion that you don't design the robot, you just let it evolve. Now, it turns out that then designing the evolution is more work than designing the robot, but still, it's an interesting idea. And so this is very academic. I'm not talking about it. So there is a little bit of something that I overlap with. So it's called here, it's somewhat odd, neurorobotics and perceptual robotics. I used to teach about neurorobotics because we're actually doing that, but because that requires all the knowledge from my winter semester course, I dropped that module. But those who were in the winter semester might know that we had some robotic implementations of those methods. And so there's a field where people do that. And this year, actually, Martin Giese is my former doctoral student. So this is an article that covers a little bit some of what I will actually be using in the first part when we use this attractor dynamics. That is considered human-like because it's sort of ideas that really describe well human behavior, and then we use it for robotics. And then robots for education and robot ethics, not very far afield. So you can look at the slides, look through them, and then you get some sense of this very heterogeneous field, very different kinds of skills and contributions. And we make a very, I circled in red a whole chapter, right? But I will maybe only do 3 slides or something like that. There is a textbook that is mostly informative about the arm stuff, the kinematics, the control, and so on, but also says some of the fundamental things. And this textbook is available as a PDF online. It's not the final version, but it's typeset, a really nice version. So you can Google that. And that will be good for the second part to get a little bit more depth. And it's very well written. I used to recommend another book. It's much more advanced and much more complicated. But this is a really nice book. It goes way beyond what we'll do in terms of the methods, but it gives you a good survey. You can Google that. Okay.